Now let us try to learn about this chlorination. In the chlorination for benzene, you add chlorine in the presence of Lewis acid I discussed earlier, say AlCl3, and you will get a chlorobenzene. Now what's the electrophile in it? As you can see, you have ClCl and AlCl3. If you think the electrophile as Cl plus, you are wrong, because the electrophile as observed is a complex which is Cl plus AlCl3 minus. Now this complex is the electrophile because this part is the attacking part on the reagent. That is, this attacks the substrate which is benzene without leaving this bond. As long as this bond is intact with this chlorine, it attacks this. So this is your electrophile. Also notice that it's a complex. Now you need not mention the mechanism again, because we have already dealt the general procedure for mechanism in the previous ones. Now let us take bromination. Now bromination is also same thing, where you use benzene with bromine in presence of say AlCl3. You will get a bromobenzene. These two are very simple. Now the case for iodination is a bit difficult. Not difficult, it's a tricky one. Let us see what's the trick in it. You know that one of the byproduct or one of the end product is, for a halogenation, let us say, if you have benzene and X2, a Lewis acid like AlCl3, let's say, you have a halobenzene and you'll get back your AlCl3, and you have one more product as HX. Keep this in mind. Now consider the case for benzene with iodine. That is, you are adding iodine plus this AlCl3. You are going to get iodobenzene plus you are going to get back your AlCl3 and HI. Look at it very carefully. HI is a very strong acid and a very powerful reducing agent, because it easily gives hydrogen in the mixture, and since it's very highly reducing agent, it tries to reduce this halobenzene form, or it tries to reduce the iodobenzene which is formed to benzene again. Now as you can see, direct method is not possible. That is, just by adding this, it is not feasible for the favoring of reaction, because it is a good reducing agent. But how to proceed this reaction? How to make this reaction feasible? The thing is, you can do two things. You know that this is an acid, so you can add either a base like say KOH or even NaOH, which converts it to Ki plus H2O in this case, and in this case NaI plus H2O. Now one more thing which you can do is, since it's a good reducing agent, treat it with an oxidizing agent. In the first case, you have treated this with base, say oxidizing agents like HNO3. You know that HNO3 and HiO3 or concentrated H2SO4 acts as an oxidizing agent, or you can even add KMnO4, hot conditions. Now these are all strong oxidizing agent, and this converts this Hi to I2. Here the oxidation state is -1 and here it is 0. Now if you see, or if you want to see which one of it is more preferable, I say that this oxidizing agent is more preferable than this one. This basis more preferable. This is because for this oxidizing agent you are getting the I2 as a product. Now as you can see in the reaction, I2 is your reactant. So from this you are getting I2 as a product. This I2 again reacts with benzene, promoting the reaction for the formation of iodobenzene. So let us see what happens for other cases. Before moving on to the further reactions of benzene, let us study the reactivity of monosubstituted benzene. That is, how the benzene reacts if any substituent is present on it. First thing is, whenever you have benzene with a ring activator present on it, it is more reactive than a normal benzene, which is in turn more reactive than a benzene with ring deactivator. Now one thing you will ask me, what are these activators and deactivators? Activators are those substituents which gives electrons to benzene ring and promote electrophilic aromatic substitution, or simply EAS. Now deactivators are those substituents which takes away electrons from benzene ring and depromotes EAS reaction. Now let us see what's actually happening here. I'll tell you one example, and by that you'll be able to know it from other examples. First, I'll take benzene with a substituent like OCH3. Say I have this. You know that oxygen is electron donator. So whenever this donates electron to this benzene ring, say this bond shifted in this direction, you are going to get double bond O, CH3, a positive charge here, and you will get a negative charge here. And this is delocalized, that is the negative charge is delocalized, and you are getting, by shifting this bond this direction, you will have double bond here, double bond O, CH3 here, double bond here, and I'll draw out the structure again. You have double bond here and a negative charge here, and one more double bond here, and this is still delocalized, a positive charge on oxygen. You will have double bond of CH3, and by shifting this bond you have negative charge here. Now observe carefully, in all these resonating structures you have negative charge at ortho and para positions. As you can see, in all these ortho and para positions, that is this position and this position and this position, electron density has increased. So these are called as ortho-para directors. Since electron density is more here, it is more possible for an electrophile to attack on this place. So if an electrophile is there, it can approach easily at this side because of more negative charge. Now let's see the case for ring deactivators. Consider a common example where you have NO2. The structure is N double bond O, O minus, and a positive charge on nitrogen. Now, as you can see, this is minus R effect group, and this one is plus R, since it's donating electrons. Since it's minus R, you know that it takes away this electrons. So you have the structure as a positive charge here and double bond N, O minus, and still a positive charge here. Now draw the resonating structure for it. You have this one, double bond N, O minus and positive charge here, and you have a positive charge here. As you can see, if you draw one more resonating structure, you'll have the same compound as this one, where you have positive charge on this carbon, double bond N, O minus. Now observe carefully. Because of presence of this NO2 group, positive charge has increased on ortho and para positions. That is, at these three positions you have more positive charge. As a result of it, it's not feasible for an electrolyte which also has a positive charge to attack on this side. So as a result of it, we say it as ring deactivators, and if any substitution has to take place, the only possible position is meta position, so we call them as meta directors. Now let us look into the examples of these ring deactivators and orthopara directors and ring deactivators or meta directors. Now let's have a look at the ring deactivators and ring deactivators. First thing you need to note is that all ring deactivators are orthopara directors. Here I have examples for ring activators where you have plus R groups or plus H groups. Now for these you can even have minus I or plus I, or for this also. So basically plus H comes under CH3. There is no need of saying it's minus I. See here, you have examples like OH, OCH3, OCOCH3. Observe that this is ring activator because oxygen here has lone pair of electrons and this able to donate to the benzene ring. Also this dash indicates that it's attached to benzene ring, PH for all these compounds. Now I have not written for this. This just indicates the substituents here. Now here also the same thing. It's donating its lone pair to it. Also one thing you need to note is that this would be the better orthopara director because it's donating electrons even more faster or more easier because of presence of CH3 group, which acts as an electron donor. And if you take this one where you have C double bond O attached to here, it's in cross conjugation basically. That is, this O is in cross conjugation with this C double bond O, resulting to formation of this one. But it is still ring activator because it's able to donate these electrons to it. Because of two cross conjugations possible, it is comparatively a slight less ring activator. And we have the same case with NH2 or NCOCH3 and this one too, this CH3 or this group. These are by virtue of their plus H group or plus H effect, and all these are ring activators by virtue of their plus R effect. Now one more thing you need to note is that O, C double bond O, CH3 is ring activator, whereas C double bond O, OCH3 is ring deactivator. This is because pH ring is attached to C double bond O here, and C double bond O is electron acceptor. That is, if you take a pH ring here, it tries to take away its electrons because of presence of this double bond O here. That is, this being a very polar, you have positive charge on this carbon and it tries to take away electrons here to satisfy its positive charge. So let's have a look at what other group which are ring deactivators. Now we have told that all ring activators are orthopara directors, but Ring deactivators can be ortho-para-directors or can be meta-directors. Now let's first see the examples for them and let's try to investigate the reason for that. First, in meta-directors we have NO2, SO3H, NO, COX or CM. Here note that X is any group like OH, or it can be CH3, or it can be any other group like say another pH group. Now these are meta-directors by virtue of this -R effect. As you can see, we have already explained this before. This nitrogen tries to take away the electrons towards itself because you have double bond O here, and oxygen being more electronegative takes away its electrons. If you look at X4-3H, you have two S double bond O's, so you have more electrophilic site here. As a result, it tries to take away electrons, creating a positive charge to the ring at ortho and para-directors, as we have discussed it before. Now the same is the case with NO. Now the structure of NO is this one. As you can see, this double bond O, oxygen being more electronegative tries to take its electrons, and you have this structure with negative charge on oxygen and positive charge on nitrogen. As a result of it, this tries to take away electrons to compensate its positive charge. Now let us come to ortho-para-directors but still ring deactivators. Remember, it's very important thing. The things that comes here are halogens like fluorine, bromine or iodine even. I'll tell you the reason for it. You know that halogens are strong -I groups because they have more electronegativity. And one more thing is that they are +R groups. Since they have lone pair of electrons, they show donating capacity of the lone pairs. But the -I for halogens is greater than +R. This is where you have to keep, or you have to understand. I'll tell you the reason for this. As you see here, these are larger in size. As you can see, for example, take iodine. It has very large size than say carbon, and effective overlap between these two is not possible. That is, the pi bonds are this much and its pi bonds are very large. So effective overlap, which is a favorable factor for stability or for delocalization, effective overlap is not possible here. As a result of it, -R effect is not significant in case of halogens. Also, these are not much donating capacity because these have more electronegativity and they are a bit reluctant towards donation of their lone pairs. As a result of it, these are not ring activators, and you have -I for them greater than +R, so these are ring deactivators. So here you need to keep in mind is that all ring activators are ortho-para-directors, and all ring deactivators need not be meta-directors. They can be either meta-director or they can be either ortho-para-director.